Hello, my name's Relevant. Welcome to the show. This is Do All the Things, and on today's episode, can I reverse engineer this executive decision maker, a kind of electronic magic 8-ball, without actually opening it? Can I guess how to build this circuit? I got two? Stay tuned to find out. According to the Value Village tag, I purchased this thing in 2009, but it is much older than that. My guess would be like 80s, maybe 90s. And it's pretty simple. It's just, you press the button, theoretically you ask it a question and it gives you an answer. Oh, definitely. I didn't ask it a question, but the answer's definitely. I saw this thing sitting on the shelf one day, and I remembered it existed, and I'm like, well, heck, could I build that using my knowledge of electronics and my design methodology? Can I make something like this? I think I can. I have an idea. Like, it seems like it could be pretty simple, actually. And, you know, taking a few guesses on what might have been in here, there's one interesting clue. So if we press the button, it oscillates. And then it stops on an answer. But we can hold the button as long as we want and continues to oscillate. I guess, you know, warming up those dice a little bit longer. But you also noticed when I took my finger off the button, it seemed to oscillate longer before it started to slow down. That gives me a clue that they're using capacitance to kind of dictate how long that oscillation happens. So, how do we build this? Well, we're gonna have to start with some sort of oscillator. Let's bring in the breadboard. Now, we want to build this for 9-volt spec. It takes a 9-volt battery, so we want some higher voltage components. And of course, I got to bust out one of my favorite little components to work with, a Schmidt trigger inverter. In this case, I'm using a Toshiba TC4S584 because it can handle the 9 volts, no problem. And we will throw together a quick relaxation oscillator. Just guessing at some values, I'm going to use a 0.1 capacitor with a 1 meg resistor. Let us hook up some power rails. I need some way to see the oscillation. Let's get an LED in here. We're gonna test off the high. Now the TC4, it has high voltage support, but it can't sink a lot of current. So a 1.5K resistor to bias that LED to keep it underneath its current sink threshold. I believe it's rated for about 8 milliamps. That 1.5K should keep it under 6. Hook up a 9-volt battery. Now when we turn it on, it should do something. That rate of blink, it looks about right. I think that looks about right. Good guess. You can tell I've played a lot with these. So how do we have that oscillation decay? Okay, let's take a guess at that. What I'm gonna do is I'm gonna disconnect the positive power. I'm gonna get a button. I'm gonna set it up all the way down here so that we can control it regardless of where other stuff is positioned. This button will power it now. And now we're just gonna stick some capacitance across this power rail. The theory being that when we hit the button, it will charge up the capacitor a bit, and then as the capacitor discharges, the oscillation is going to slow down and eventually stop. It seems to get faster, not slower. We might have a circumstance where the LED is sinking out the current. Let's try something different. I'm going to buffer that LED, just using a 2N7000 MOSFET. Going to get it on the negative rail over here. We'll jumper signal from the output to the gate of the MOSFET. It's brighter now because we can bias it a bit hotter. Oh wow, the oscillator is running a long time off of 470. Okay, we've created a monster. It's still going. Anytime now, bud. Our capacitor might be a bit big for the application now. All right, let's significantly downsize that capacitor. That's a 22U. Okay, I don't know if the camera's picking it up, but it's a more favorable result now, except for the fact that it does still clock faster as it runs out of power. That's not necessarily a bad thing. Either way, this is probably good enough of a methodology to get our oscillator the way we need it to be. So let's move on to the next stage. How do we get it to juggle through different outputs? Well, we're just going to use a good old-fashioned CD4017. I don't have much use for a 4017 because they're not fast enough for really fast clock signals. There's a circuit I was designing up to 1 megahertz. Barely cut it. Also, the edge triggering, blah, blah, blah. I won't get into it, but it does have high voltage support, and for something this slow, it could be a sweet spot. We'll get power connected to it, and maybe we'll move our button up to that same rail just so it's easy. Now, in order to get the 4017 working, we got to connect a whole bunch of pins. And of course, the Texas Instruments datasheet doesn't explain it very well. We need to pull a pin called clock inhibit low. Clock inhibit has it ignore the clock signal when it goes high. Then we're going to take our output from our oscillator, put that into the clock input. Then we're going to need a whole whack of LEDs. We're going to go with 9 instead of 6 because we have enough for it. We're just going to create a bank of them over here. Now I've put all the LEDs on the same, one of the spare bus line strips going down here because no 2 LEDs, there's never going to be more than 1 LED operating at the same time, so we can common cathode bias them. So somewhere up here, we're simply going to go strip to ground, 1.5K resistor, 6 milliamps. But at any point in time, if I take a high, a positive signal, so now we have to jumper all those to the outputs of the 4017. It's a little annoying because they're all over the frickin' place, bud. So for example, number 1 is a 0, is a pin 3, 2 is 1 pin 2, 3 is 2 pin 4. 4 is going to be 3 on pin 7. I think you see where I'm going with this. So I'm just going to go ahead and hook this all up. We're using 9 positions out of 10, going down to 8. They start at 0, right? So then we just have to take a reset signal, which is going to be 9, so that it cycles over once it hits past 8, and connect that to reset pin 15. Okay, that should work now. Looks like a bit of a mess, but... And my button's hiding. Oh. Whoa. I think we need to improve on this just a little bit more. And getting rid of this LED. I feel like I want the oscillator to oscillate just a bit faster. What happens if we replace the 1 meg with a 470K? Oh yeah, that looks better. I need to dig out this switch though. It's no fun tucked in there. Oh heck, bud, here's a positive rail right here. I think we want a little bit more capacitor. That's a 22U. Let's try a 47U. Yeah, that gives roughly a desired effect. So if you haven't guessed, green is yes, orange is maybe, red's gonna be no. This is kind of fun. Just keep tapping that button, bud. And let her give her go. Is this circuit working? Uh-huh. Is it as good as the decision maker? Maybe. Hey, it's accurate. We'll give it that. How about some sound effects? This thing beeps after all. Grab a random 12 volt beeper. This is an AI 1223 TWT. I think it's the cheapest 12 volt beeper on, was it Mauser I got this one? We're gonna go back to our 2N7000 here, which hilarity might ensue with this, because the MOSFET is functioning unpredictably or predictably incorrectly with the kind of signal that the oscillator's putting out. Not quite the effect we're going for. It doesn't help that I wired it backwards. There we go. Okay, what? Oh boy. It screams in pain. It's still whimpering. No. It is not happy. Oh boy. Oh, how do we solve that problem? Like the first thing to do is to confirm exactly what kind of output the inverter's putting out. Because once we cut power to it, it gets separated from the positive source. So what is this guy doing? So the meter says it's putting out 4 volts, which is just probably because it's pulsing. It's kind of having a PWM effect. And then, yeah, it slowly sinks down. Well, I'm hazarding to guess that we do not need a whole heck of a lot of signal to drive that MOSFET. My guess is if I put something like a 100K resistor to the gate of that, it should still work. Yep. So let's clean this up a bit, because we want the lowest impedance load possible on the output of that oscillator so that it doesn't affect the oscillation. I'm just having a problem locating the diode I was just working with, bud. What the We're gonna try once again. Now that I know that all the impedance loads I'm putting on output is not affecting it, I'm gonna put a diode in here so that we only have high signal. Still. Okay, so I chucked a 5.1 volt Zener diode on there, and so when the output reaches a certain threshold, it can't go past it. Still not as clean a result as we want. Well, it's definitely a silly situation. And it's probably due to the fact that the relaxed oscillator is just a little bit too relaxed. There's probably something a little bit more intelligent going on in here that, has a definitive cutoff when it hits. The cycle randomization aspect of things was relatively easy. Like easy, easy, easy. I didn't expect the sound effects to be the hardest part of the circuit. Hey, why does it keep stopping on that yellow now? What if, and hear me out here, what if we try reversing the phase that we're controlling on the oscillator? What if, instead of switching the high, we switch the low? Very similar effect, though what effect is that going to have on the beepinator? It has the effect of it getting stuck on because we're removing the low, which will turn it off. Let's switch to P channel. Probably going to have the same effect. What? Oh, now it's musical. Except that it won't shut up. That's what's fun tinkering with circuits sometimes. When the circuits go unstable and have like unpredictable results, it's just like, oh, that's not doing what I expected to do, but that's hilarious nonetheless. So I'm gonna play with the capacitor resistor value on the oscillator to see if I can get it to respond a little bit differently. We will up the capacitance to about 1U, which is gonna be super slow unless we greatly increase the resistance. Oh geez, even with 100K. 22K gives us similar to what we had before. The idea being that with that smaller resistance, if we burn out what's left in the oscillator faster, maybe we'll have more reliable control over the MOSFET. Now we're gonna go back to positive switching. Yes. That is what's happening. So we got a diode and a 10K pull-up. Makes for quite the afternoon. What happens, MSPA06, what happens if we replace the MOSFET with a transistor? See how differently it responds. Putting 1K buffer on the input. Oh boy. It's like some sort of frog version. How about a 10K buffer, 100K pull down? You know what's funny? I had, a bunch of 22Ks in here. 47K. This can't possibly work. 10K, 10K. They'd conflict with each other. Yeah. They cancel each other out. We got better results with the MOSFET bud, which is probably why I prefer working with them. Yeah. You know, we got a 22K pull down right now and a 1K buffer, and it's a little frog chirp at the end, but it's a lot better than it was. I almost feel like I want a little bit more than 47. I thought I had 100U accessible. I do, but it has short legs, can't reach the ground. Let's try a 220. Oh, we're back to that again. Let's try a 100U. Let's go back to a 22U. You know what? That's not bad. It's quick. You know, you can hold if you want more. But it's more abrasive. It's more like the, Screamo Core metal version of this thing. This one's a lot more softer and pleasant. Ah, yeah. So now that we've, I'm kind of done YOLO bombing parts into this. It was a bit of an experiment. I didn't know what was going to happen. Let's see what's actually inside this thing without breaking the connector. Holy frick, bud. Wow, the connector. After all these years of existence, this connector is just chowdered up on me. Okay, looks like the plastic's soft enough I can just pop it back into place. How do we get this open, sir? Oh, okay, oh, look at that. It is, I don't recognize this. I don't think I've ever opened this before. You've got just a very rudimentary surface mount button. And, oh yeah, there's fingerprints in here. Yeah, that's not gonna wear out over time, isn't it? 2.2 UF and some Toshibas. TC4017. Well, I got that right. But what's this thing here? A TC4011. And there's no other ICs on here. What's a 4011? A 4011 is a NAND gate, bud. Quad 2 input NAND gate. So that's just basically our typical Kuhn chip, I think. But an 11. Inverted buffers. You know what? Knowing what I know, there is a way to get oscillation using NAND. It's a little trickier, but hey. The funny part is, this is pennies of components here. By today's standards, made in China, this would cost nothing to build. You could make a profit out of it at $2.99. Date codes on the chips. We have a 1989 and a 1990. I believe that will put this early 90s. I suppose I could reverse engineer this. I don't feel like it though. But I'm willing to bet they do pretty much the same thing, a relaxed oscillator, except using NAND gates. And probably using methods I'm familiar with for building horn drivers, which is what they're doing here probably. A couple of those gates are probably just to generate the beat for this. That's a 1K, that's a 100K, that's a 56K. Oof, what is this? Brown, green, green. Well, that's brown, green, orange. That's 5, orange, 15K. I think brown, green, green is going to be 1.5 meg. 1.5 green times 100K. Yeah, that's 1.5 megs. What do we have for capacitors here? Those 1.5 megs are probably on the oscillator. Oh, they haven't got number codes. Just straight up 0.022. Oh, this one's number code 392. So that's a 0039? 0039? Yeah, because a 472 would be a 0047. So the effect that they're going for is very similar. They have an oscillator with NAND gates, and they probably only need 2 NAND gates to do that. And then they're gonna have another set of NAND gates to do an oscillator to generate the beep, 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 beep. And then bam, a 4017 to sync those LEDs. So my design's simpler, actually, quite a bit simpler. But, this one's got more polish and finesse and just, it's generally nicer than, If we built this, I'm not gonna build it, I have no point to build it. We'd have to use a green box and name it after some kind of frog. All right, well, I think that's it for today. Like, I can guess on how this is done. I have a pretty good idea. I don't know that I wanna film myself building it. This video is gonna run long for such a pointless little project. This is basically, can I predict how they did this, reverse engineer it? Okay, buds, I couldn't help myself, but have to try to reverse engineer this because I got curious, because I was familiar with the concept of using NAND gates to build an oscillator. Based on this design, this is a couple inverters used to drive a piezo. A piezo with feedback. We won't get into that, but that's basically a piezo beeper, kind of like what we see on the bottom here, generating a frequency to drive it. The basic core concept here is this 1.8 meg is the feedback, and it has to connect the two sides of this, and then we have a capacitor that goes from the front all the way to some capacity to the back. That's based on this, I came up with this, which I'm fairly confident is what they got going on in here. We have our feedback resistor here from the output of that to the input of this. And then we have our charge capacitor going from the output here. Now, because there's no Schmidt trigger, we kind of need a fully inverted capacitor situation. So this is going to work very much like a relaxed oscillator will, with the inversion coming out the front, changing the state of the input. But unlike the Schmidt trigger, we kind of need the capacitor to get inverted too. So like, well, you know, go do your own research. I'm not interested in explaining more how this works, but the thing with the NAND gates is instead of cutting power to it like I was in the inverter, you have a second pin. You can use one for the function and one to enable or disable. So if we stick a high signal on here, it enables the oscillation. That's basically what we're going on here. Now they have a 1.5 meg here and an 022 here. I just have a 470, 01. Pretty much the same difference other than the decay factor might be different. Now what's not seen here is the Zener regulation, which is why I have this 1K here that they don't have in the circuit. Because if I just run raw dog positive to this input pin, it seems to overheat the Zener diode. This is where they have the 2.2U. That is where they have another 1.5 meg. The idea being, we charge up this capacitor, but once it's at a charged state, this needs so little microamps, it just pretty much keeps running. So we need to have some sort of high impedance resistor here to slowly bleed out the current that's charged. We end up with functionality like this. Bam. Pretty much just what the doctor ordered, and the beeper's working properly too. Because instead of just cutting power and having an awkward decay, well, it just disables the oscillation. So the beeper, whatever's running the beeper, gets a very solid signal as to what it should be doing. Now I'm using a beeper with built-in oscillation. It just makes the sound when you hook it up. They would otherwise use that identical oscillation circuit to generate a more high frequency oscillator to drive that piezo using the other half of the NAND situation. Now the NAND I'm using is a 74HC00. That's your common 7400 base bog standard NAND chip. I found the fundamental difference between the 7400 that I'm used to and the 4011 is the 4011 CD logic rated for higher voltage. So this guy can run right off 9 volts. This guy doesn't. So I need a Zener diode. I need some bias for it. I just arbitrarily picked a 330 ohm. Runs fine. It's getting 5.1 volts. Had to add that 1K on there. And with only a 1U resistor, because I didn't feel like going to see if I had a 2.2. And now it pretty much works the same, except it doesn't have the decay. Now I imagine that might have something to do with how my voltages are here. I'm willing to bet, okay, well let's try it right now. Let's put a 2.2 in here instead of that 1U. Let's get rid of the 470. I think I have 1.5s in stock. All right, chuck her a 1.5 meg feedback resistor in here. Oh, what? What did we do wrong? Ah, okay. Yeah, a touch faster, but pretty much the same effect. Still not decaying though. I wouldn't be surprised if we found ourselves a 4011, chucked her in here running raw dog off 9 volts. We would get that decay we're trying to get here. Because I don't really see much going on here. Like, I didn't map this out much. I just I know how to make a NAND oscillate. Let's chuck her in there. Kind of just looked at some of the values here. And yes, this capacitor is that charge for the button press, 2.2U. And then I just kind of looked at a couple of things. Oh yeah, it has a pull down. Oh yeah, it goes from here to there. But yeah, there you have it. Executive decision maker, electronic 8-ball, reverse engineered. There's roughly the oscillator schematic, converted to 9 volts if you want with a 4011. Not going to show you how to hook up the 4017. That's in the data sheet. It's stupid simple. And then I'm also omitting the oscillator. The oscillator would be the same thing as this. And I'm also omitting the beeper oscillator. It would be the same thing as this, but with different values to get a high frequency. That 0039 is likely what's generating the frequency. And the 470K, well, let's see what we got here. We got 100K here and a 56K. You know what? It looks like I simplified things. It looks like what they're doing is more similar to this, where we have two different kinds of resistors, kind of. It looks like that might be the 100K and that might be the 56K. Just make these NAND gates instead, with the enable pin going to the signal out of the other half, and that's the 0039. No feedback, and then just directly driving this, there is a 1K, or is it a 10K? Yeah, a 1K resistor coming off the input onto the positive side. Well, hell, are they doing that same thing for the main oscillator? Maybe that makes a big difference. Yeah, that's what's going on in here. Okay, let me just quickly restructure this. 1.5 meg and a 15K. I'll use a 10K. Wait. Okay. Okay, clearly I'm not understanding something about how they've got this wired. Oh. No, I've broken it. Okay, I was tinkering on some components here without like really trying to map out how they're doing it here, and just kind of guessing based more on this design, which doesn't quite work. Well, I couldn't get it to function any differently. The lights blink stupid because the beeper is interfering with the output, but it otherwise goes normally with the beeper. So for one final little finishing touch, I'm gonna try to proper buffer this beeper with the MOSFET again. We could use the remaining gates on here just to put like a double inverter to get the same effect. But yeah, now there we go, something a bit more proper. Looks and sounds better. Lettuce and tomato, just officiate this with a 2.2U. And now it even has about the same time delay. A little grind at the end. But anyway, that's that. I tried to guess at how it was done. With my knowledge, I was a bit wrong, but I got something working. A nice frog friggin', I don't even know what to call it. And then we looked inside, see how they actually do it. Using NAND gates, we put some NAND gates into this, and now it's just kind of like, yeah. Works good now. We would just need a higher voltage NAND gate to officiate it if I wanted to build something like that. But I don't have to because I got the real thing here. So, I hope you enjoyed this. If you did, stay tuned. I like to play with circuits sometimes. Got another novelty circuit coming. This is going to be really interesting when I finally finish deciding how I want to set it up. Speed up that oscillator and bring it down to only 3. And to be honest, I think I prefer it this way.